And we use a system of numbers to describe those things. And those numbers are called the quantum numbers, okay? So quantum numbers describe the physical properties of an electron within an atom. And these are wave properties, okay? Wave properties mostly. There are some particle properties as well because we recognize electrons have wave-particle duality, okay? So you can also think of quantum numbers as an electron's address on the periodic table, all right? So we're going to put these quantum numbers together and we're going to see how they map out on to the periodic table. And they very much are like an address, okay? So the first one that we start with, number 1, is the principal quantum number. And I've already described this. The principal quantum number, N, is related to those energy levels. So I'm just going to back up really quick. We're going to back all the way through this, right? And so when we were talking about the hydrogen spectrum, okay, all of these different lines, these are all of the energy levels that are related to the principal quantum number. So in some ways, you could kind of think of the principal quantum number as let's say your state. So if, let's say this is the address, we'll call this the state that you live in. So California, for example, okay? And so now we go to the next hierarchy, number 2, the angular momentum quantum number. So this describes the angular momentum of an electron, okay? Oh, and by the way, I didn't say, but principal quantum number, I think, we talked about this earlier. It's just values, integers. 0 doesn't count. So it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, okay? So the angular momentum quantum number, L is the letter, it depends on the principal quantum number, okay? So I really like to think of this as like the city that you live in, for example. If we were thinking of this as a hierarchy for addresses, okay? So the angular momentum quantum number is dependent on the principal quantum number. And so it can take on any value from 0 all the way to n minus 1. So for example, suppose that n equals 2, okay? So then this means L, so we would say therefore L could equal 0 or 1, right? Because 2 minus 1 gives me 1. So this could include all values 0 to 1. So for example, if n was equal to 3, then the angular momentum quantum number could be 0, 1, or 2. So all we're doing is just describing the possibilities. We haven't described an individual electron yet. We're just talking about the possibilities. Okay, then now the next hierarchy, number 3, the magnetic quantum number. So that's an M subscript L, M sub L. And this could really be, you could think of this as the street that you live on, okay? And so that is based off of quantum number L. So you can see ML can be any value from negative L to L, including 0. So again, if we still had this n is equal to 2, we could have L equal to 0 or 1, okay? And then correspondingly, my ML could be negative 1, 0, or 1. So that includes that 0 right there, okay? And so let's see, instead of using, so we can use numbers for ML, we can use numbers for L, but we could also, I'm saying this all backwards. We can use numbers for L, but more commonly we use letters. So that's where this is at right here, okay? So here you can see our value of L, 0, 1, 2, 3, 4. This is as high as the periodic table goes. So technically the periodic table doesn't go, it really doesn't go past 3, okay? So this number 4 is theoretical for when we find more atoms and the periodic table has to get bigger, okay? So this is where we're at right now. So this is where the periodic table stops currently at L is equal to 3. So what do all these mean? Well, when you have 0, we often use the letter S for 0. Okay? We use the letter P for L is equal to 1, D for 2, F for 3, and because that's where the periodic table stops, what people decided the next logical thing to do would be to go in alphabetical order. So G, H, I, J, K, etc. But we're not there yet because technically we only have S, P, D, and F. So these things they actually stand for something. So S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fine. So these are historical names that are based on the spectra, based on the way that the spectra look. So I'm not going to get into a whole lot of detail of why it's sharp, principal, diffuse, and fine, but that's where those letters come from in case you're curious, okay? So 0 for S, 1 for P, 2 for D, 3 for F, you should know that, okay? So now we can also build up this a little bit. And so as it turns out with the L values, okay, if I also look at the value of ML, which is based off of L, okay, so it can only be 0 when L is 0. And here's how this works. That is 1 ML number correspondingly 1 orbital per shell. So I'm going to draw an arrow to this thing. And we're seeing actually how these numbers, it's kind of like a computer code. These numbers are not very intuitive. So they really are based off of like a computer code in some ways, okay? So for L is equal to 0, there's only 1 orbital per shell. Well, what's a shell? Well, that thing that I just described. S shell, P shell, D shell, F shell, okay? So just 1 orbital per S shell. Well, what about L is equal to 1? Well, when L is equal to 1, ML can be -1, 0, or +1. That's 3 ML numbers, and then check it out. 3 orbitals per shell, 3 p orbitals per shell from the 3 ML numbers. So now you notice the next one is 5 and then 7. So how do we get 5 and 7? Well, when L is 2, I can go -2, -1, 0, +1, +2. Yep, that's 5 ML numbers, 1, 2, 3, 4, 5, correspondingly 5 orbitals per shell. And I'm going to describe where these angular nodes come from in a moment, okay? So we'll get here in a moment where these angular nodes come from. And then finally, you might have guessed this, when L is 3, -3, -2, -1, 0, 1, 2, 3. I know that's hard to read, but that is 7 numbers. 7 ML numbers giving me 7 F orbitals per shell. And I'm going to describe what all of these things mean soon, okay? For now, we're just establishing the rules of these numbers, and I'm going to show you where all of these numbers manifest momentarily, okay? And so there is one last quantum number we need. So if I back up for a second, look, we had the principal quantum number, that's like the state we live in. The angular momentum quantum number, that's like our city. The magnetic quantum number is our street. So what we're missing is like our house number, right? In this analogy, that would be our last thing. So the electron spin quantum number, m sub s, this is like our house number on our street. And as it turns out in quantum mechanics, there's only 2 allowed house numbers. It's like a mother-in-law unit or whatever. +1/2 or -1/2. That's it. And what does that correspond to? Well, it corresponds to the electron spin. So this is actually a particle property of electrons. So I talked about how electrons have wave properties, but they also have particle properties. One of those properties is, as you can see this picture here, electrons spin. And this is what creates what we know as the right-hand rule. And the right-hand rule says if you take your right hand and stick your thumb up and you make it spin around like this, okay, then you have a magnetic moment pointing up, okay? And so because I only have one right hand, if I want to spin this the opposite way, when it spins the opposite way, I have a magnetic moment pointing down. So these electrons make these little magnets with a north pole and a south pole, just like is shown in this picture. And there's actually some evidence of that, okay? So if we take, for example, so the famous experiment was done with silver ions. So a bunch of silver ions were, I've forgotten the name of the scientist now, shame on me. But these things were shot down a vacuum chamber and passed through, so this is all in vacuum, and passed through a large magnet, okay? And as it turns out, silver plus has one unpaired electron, and we'll see what that means later on. But silver, because of that one unpaired electron, it could actually be spinning up, so it can have a north pole going this way, or it could be spinning down. And as it turns out, there's an equal probability of having both. So what they saw, oh, this was the Stern-Gerlach experiment. I just remembered that. Stern-Gerlach experiment. So what they saw was after they passed this beam of atoms through this magnet, they split. And they saw two points on a screen where those atoms were colliding with the screen. And one corresponds to the ms plus 1/2 state, which we call the spin up. And then the others corresponded to the ms negative 1/2 state, what we call the spin down, okay? And so in the silver case, because it had one unpaired electron, there's an equal probability of it being both, and so both spin states is observed, okay? Another way to observe this, although it's very, very difficult, in the spectrum, and here's hydrogen, and we recall hydrogen only has one electron, and because it only has one electron, it could be either spin up or spin down with equal probability. And so if you were to zoom in on these lines, so remember, these are the lines that we would see from the spectrum, from the different energy levels. Then as it turns out, that spin up or spin down can make just a slight, tiny difference in the energy level diagrams. And what it gives you is what we call a doublet. And that doublet corresponds to the fact that one line is spin up and one line is spin down, and they exist with equal probability. Now, as we'll see, when we have atoms with paired electrons, and maybe you have some experience in this from your high school class or another chemistry class, but electrons really like to be paired because when they're paired, you now have North Pole and South Pole and North Pole and South Pole, right? And that's very stable when I can combine the North Pole and the South Pole. And so when you see atoms like that, or molecules that have paired electrons, these, you know, a doublet like this, or like a result from the Stern-Gerlach, you wouldn't observe that. You would not see that happen, okay? So this is the experimental evidence of these spin numbers, okay? So in summary, we have principal quantum number n. That's the main one. That's where we start. Okay, that's why I said it's like our state. We have the angular momentum quantum number. That's like the city we live in. That's based off of the principal quantum number. We have the magnetic quantum number, which is like the street you live on. So, of course, that's got to be based on the city you live in. And then finally, we have the electron spin number. That's like your house number on the street that you live on. And there's only two possibilities. plus 1/2 or minus 1/2. Okay? So let's see